All right, I left you on an example asking you to solve a differential equation. Truly, the differential equation I left you was x times the derivative of y plus y equals x squared y squared, but that's in fact the exact example I had done previously. Hopefully you read between the lines and saw that I had intended for you to do this one instead. So in this case, this is Bernoulli with n equal to 3. So we use the substitution u equals y to the 1 minus 3. Now 1 minus 3 is -2, which means that y is equal to u to the -1/2. And dy dx then is -1/2 u to the -3/2 times du dx. Plugging this into the differential equation gives us this thing that looks nastier, but when I write it in standard form, this is now a linear differential equation. It's linear in u. I can solve this using integrating factor, multiplying everything by x to the -2, and then integrating both sides as we've been doing. We end up with that y is that u is -2x squared natural log x plus c x squared. Now remembering that y is equal to u to the -1/2 means that y is equal to -2x squared natural log x plus cx squared to the -1/2. And we've solved this differential equation. Again, we started with a differential equation we didn't know how to solve. We used a substitution, which turned this into a differential equation we do know how to solve. All right, so now let's revisit the appendix. We've been talking about matrices. Last time we talked about using matrices to solve systems of equations. So I'm going to start with another definition. Let's let A be an M by N matrix. We say that lambda is an eigenvalue of the matrix A if there exists a non-zero vector K such that AK is equal to lambda K. And here we say K is an eigenvector associated with lambda. So it's great to have the definition. The definition actually gives us an idea about how to find these values. So we'll make a remark here. The only requirement that we have is that for some vector K, AK is equal to lambda times K. Which means that AK minus lambda K is equal to 0. Now, if I factor the K out of here, this would be A minus lambda times the identity. K equals 0. The identity popped out here because remember we're dealing with matrices here, not scalars. If I factor out the matrix K from here, I'm left with just a scalar, and I can't subtract a matrix with a scalar. I need something to turn this into a matrix. K times 1 is just K, and in the case where 1 looks like a matrix, still works. A consequence of this, if a minus lambda I times k equals 0, and k is not 0, means that a minus lambda I equals 0, which is a little bit awkward. So what we're looking for is the determinant of a minus lambda I being equal to 0. So this is going to tell us how to find lambda. Once we find lambda, then we know a and we know lambda. We just need to find the k. So that's going to be our approach here. Let's look at a couple examples. Let's start with, say, A is the 2 by 2 matrix 2, 0, 0, 1, and we want to find the eigenvalues and eigenvectors associated with those eigenvalues. So to find the eigenvalues, we're going to find lambda, so the determinant of a minus lambda I is equal to 0, which means the determinant of a was 2, 0, 0, 1, and we're subtracting off lambda times 1, 0, 0, 1, and we need that to be equal to 0. So the determinant of 2, 0, 0, 1 minus lambda 0, 0, lambda needs to be equal to 0, which means the determinant of 2 minus lambda 0, 0, 1 minus lambda needs to be equal to 0. The determinant of a 2 by 2 matrix is 2 minus lambda times 1 minus lambda minus 0 times 0. And I need that to be equal to 0. This is quadratic in lambda. So we get solutions lambda equals 1 and 2. So we have two eigenvalues associated, or two eigenvalues of this matrix. Now we need to find the eigenvectors. Now the eigenvectors are the vectors k, so that ak is equal to lambda k, or a minus lambda I k equals 0. So let's say we'll do lambda 1 is 1 and then see what happens. If we're letting lambda be equal to 1, then we have 2, 0, 0, 1 minus 1 times 1, 0, 0, 1 times k is equal to the 0 vector. And so we get 2, 0, 0, 1 minus 1, 0, 0, 1 k equals 0. Which gives us the matrix 2 minus 1, 0, 0, 1 minus 1. So we have 1, 0, 0, 0, k must be equal to the 0 vector. Now remember, k is its own vector. It has components u and v or x and y, whatever you want to call them. We will call them x and y just for the sake of consistency. We're looking for values of x and y so that this always gives 0. You'll note, based on our solving equations last time, this is equivalent to 1x plus 0y equals 0, and 0x plus 0y is equal to 0. Now, I need to find values of x and y which hold this true. The second equation is always going to be true no matter what you pick for x and y. The first equation, though, requires x to be 0. So x must be 0, but we'll observe that it doesn't matter what y is. Y gets zeroed out. So y can be anything we want it to be. We can choose any number for y to represent this. If we can choose any number for y, keeping in mind we can't choose the 0 vector, I'm just going to let y be equal to 1. And what we have is the eigenvector associated with the eigenvalue of 1 is the vector 0, 1. That was only one of them. So now we choose the other one. Let lambda be equal to 2. If I let lambda be equal to 2, then I get that 2, 0, 0, 1 minus 2 times 1, 0, 0, 1 times k must be equal to the 0 vector, which simplifies to 2 minus 2, 0, 0, negative 1, k must be equal to 0, or just 0, 0, 0, negative 1, k must be equal to the 0 vector. Again, rewriting this as a system tells us that 0x plus 0y must be equal to 0, and 0x minus y must be equal to 0. This tells us the value of y must be 0, but I have freedom in choosing an x value, so my eigenvector associated with this is going to be 1, 0. Again, this equation tells me it doesn't matter what I plug in for x, so I can plug anything I want to. And y has to be 0. That's the only way the second equation is going to be 0. If I could choose anything I want to for x, I'm going to choose it to be 1. So we have the eigenvalue of 1 has eigenvector 0, 1. And the eigenvalue 2 has vector 1, 0. Let's do a couple more of these. Let's say we have the matrix 3, 4, negative 1, 7. There was something very special about the last example, which is why it came out so nicely. There's no reason to believe that will always be the case. So let's do this one. We need to find the eigenvectors first, and then we find the we need to find the eigenvalues first, and we need to find the eigenvectors associated with the eigenvalues. So step 1 is going to be to find the values themselves. Now these are values so that the determinant of a minus lambda I is equal to 0. So we're looking for 3, 4, negative 1, 7 minus lambda 0, 0 lambda. I need that determinant to be equal to 0. So I have 3 minus lambda 4 -1, and 7 minus lambda. That determinant needs to be equal to 0. So 3 minus lambda, 7 minus lambda minus -1 times 4 must be equal to 0. Multiplying this out, I get lambda squared minus 3 lambda minus 7 lambda is minus 10 lambda. And 3 and 7 make 21. And then I have -1 times 4 is -4. Minus -4 means plus 4. And that equals 0. And so we get lambda squared minus 10 lambda plus 25 equals 0. And we have a hiccup here. This factors into lambda minus 5 quantity squared, telling us that we have 2 eigenvalues here, but they are the same eigenvalue. They are a repeated eigenvalue. We saw in the previous example what happens when we have 2 distinct eigenvalues. And in this example now, we have a repeated eigenvalue. Our next step is going to be find k associated with these eigenvalues. That is, find k so that k is equal to lambda k. That is a minus lambda I. K is equal to the 0 vector. 3 minus 5, 4, -1, 7 minus 5. K equals 0, which is 3 minus 5 is -2, 4, -1, and 2. K equals 0. This gives us the equations -2x plus 4y equals 0 and -x plus 2y equals 0. Now we need to choose values of x and y which make these true. Any value of x and y which make these equations true will work. And I'm going to point out that this top equation is just the bottom equation times 2. So the top equation doesn't really add anything. It doesn't help us in any way, shape, or form. I just need to find values of x and y so that this is true. So I will arbitrarily let y be equal to 1. If I let y be equal to 1 here, then x, it must be equal to 2 for that to be equal to 0. So we have our first eigenvector. Lambda 1 of 5 corresponds to a k of 2, 1. Now we need to handle this repeated value, right? This didn't happen in the previous example. The previous example, everything came out nicely. They gave us distinct eigenvalues, and those distinct eigenvalues gave us distinct eigenvectors. But now, if I set up to find this k, again, using the same lambda, I'm going to end up with the same equation because I haven't changed anything. So we need to change something about this. So if these values are distinct, we're just going to keep on. We have a different value here to plug in for lambda, which is going to give us a different relationship between x and y to make sure that 0 holds. If they're repeated, however, which is what we have here, our first was a minus lambda I, k equals 0. We did that already to find the first one. To find the second one, we're going to do a minus lambda I equals k1. And that's going to be our approach. Instead of setting it equal to 0, we're going to set it equal to K1. For reasons that are linear algebra related, we don't care about them for this class, but we still need to be able to find the eigenvectors. So in this case, we have, piggybacking off this, but not setting it equal to 0, we have -2, 4, -1, 2, K2, and that's going to be equal to K1, which is the vector 2, 1, which gives us the system -2x plus 4y equals 2 and -x plus 2y equals 1. You'll note that once again, the top equation is just the bottom equation times 2, so it's not helpful. I just need to find values of x and y which make this true. So letting y in this case be equal to 1. If y is equal to 1, then I have -x plus 2 equals 1. So subtracting 2 from both sides, I get -x is equal to -1. So x must be equal to 1. And so that's our second eigenvector. A quick note, if I do a 3x3 here instead, there's nothing that limits this to 2x2s. If I do a 3x3 here, say A is 0, -1, -3, 2, 3, 3, -2, 1, 1. And I want to find the eigenvalues and eigenvectors here. Still going to set up the same thing. I need to find lambda, and then I need to find the k that corresponds to each of those lambdas. So to find the eigenvalues, I'm going to set up the determinant of a minus lambda I equals 0. In this case, I is a 3x3. So I'm taking the determinant of 0 minus lambda, -1, -3, 2, 3 minus lambda, 3, -2, 1, 1 minus lambda. And I'm setting that determinant equal to 0. Finding this determinant is non-trivial, but that's okay. We have negative lambda times the determinant of 3 minus lambda, 3, 1, 1 minus lambda, minus -1 times the determinant of its minor, 2, 3, -2, 1 minus lambda, plus -3 times the determinant of its minor, 2, 3 minus lambda, -2, 1, and I'm going to set that whole thing equal to 0. So I have negative lambda times 3 minus lambda, 1 minus lambda, minus 3, plus 2 times 1 minus lambda, plus 6, minus 3 times 2 minus -2 times 3 minus lambda equals 0. Multiplying all this out, we get lambda cubed plus some other stuff is equal to 0. So we end up with an equation which is cubic in lambda. This means that we have either 0 distinct it means we have either 1 distinct eigenvalue, 2 distinct eigenvalues, or 3 distinct eigenvalues. In this case, one of the eigenvalues that we get is -2. And I will let you find the other 2. In terms of finding the k associated with that eigenvalue of -2, if I let lambda be equal to -2, I am now solving 0 minus -2, -1, -3, 2, 3 minus -2, 3, -2, 1, 1 minus -2. Okay, equals the 0 vector. Cleaning this up just a little bit, I have 2, -1, -3, 2, 5, 3, and -2, 1, 3. Okay, equals 0. And I have to find values of k that make this true. You'll notice this bottom equation is identical to the top equation, just multiplied by -1. And so I get the equations 2x minus y minus 3z equals 0, and 2x plus y plus 3z equals 0. And I have no information about z except that it's equal to itself, I guess. Let's clean these up a little bit. I can subtract these two equations. Get for the top equation 2x minus y minus 3z equals 0. When I subtract the top equation from the second equation, I get 2x minus 2x, that goes away. Y minus -y is 2y, and 3z minus -3z is 3z plus 3z, or 6z, and that equals 0. And the only thing I know about z is that it is, of course, equal to itself. So now I need to find values of x, y, z that make this true. You'll notice x and y both depend on z. So if I choose z to be 1, this equation becomes 2y plus 6 equals 0. So y has to be -3. And in this case, I have 2x, y is -3, z is 1. And so I get that x has to be 0. And so we found the eigenvector associated with this eigenvalue. And we repeat that for the other two roots. If ever we get a repeated root, the first time I set it equal to 0, the second time I set it equal to the eigenvector that I just got, and so on. All right, that takes us through the end of today. I will see you next recording.